Okay, for Chapter 5, the good news is that most of you did extremely well on it because only 3 questions popped up as the most missed questions. So the first one I'm going to go over is number 11. And part of the problem with number 11, as many of you realized, is you're missing information, and that was my fault. So I'm going to chalk this one up to not that you didn't understand, but that I didn't quite give you the info. But obviously the key phrase here is collected over water, and I'm telling you right now, whenever you have a problem that involves collecting it over water, you will always be given 2 things. The total pressure, which was clearly 742 torr here, and then you have to be given the pressure of water. And in this case, the pressure of water was missing from the problem, although if you looked back at previous homeworks or just Googled it, you would have found it. And the pressure of water at 23 degrees Celsius is 21.1 millimeters mercury. So whenever you have a problem that's collected over water, you must subtract the total pressure and the pressure of the water in order to segregate out just the pressure of the gas. In this case, you get 720.9 torr as the pressure of the gas. No, that's not the correct sig figs. It should be 721. But it won't make that big of a difference in your answer. If you look, you know the pressure of the gas now at 23 degrees Celsius, which was the temp that the sample was collected over water at. And you know the volume, which was 85.6 milliliters. And what they're asking you is what's the volume at STP? And remember, STP is 2 values. It tells you the pressure and the temp. So I used the combined gas law. On the left side, I put all the information when the sample was at 23 degrees Celsius. And on the right, I put all the information for when the sample was at STP. And then I just solved and got 74.9 milliliters. Now the second question that was most missed is number 18. In a mixture of 10 grams each of hydrogen, oxygen, argon, and krypton, which gas exerts the greatest pressure? Partial pressure. And remember, the partial pressure of a gas is equal to the mole fraction of a gas times the total pressure. And since all these gases are in a mixture, they'll all have the same total pressure because they're all at the same conditions. So what this really comes down to is the pressure of a gas, the partial pressure of a gas, is going to be equal to the mole fraction. And the mole fraction is moles of a gas on top over total moles on the bottom. And the key is that they all have 10 grams. But how do you get from grams to moles? Of course, it's molar mass. So the key is you would have to convert each one of those, so the 10 grams, that's a terrible 10, but 10 grams, to moles. And remember, if it's hydrogen, for example, its molar mass is 2. But if it's oxygen, its molar mass is 32. And what gives you a bigger number of moles? 10 divided by 2 or 10 divided by 32? And the key is the smaller the molar mass, the more moles you'll get, and the more moles you'll get, the larger the mole fraction, and so the partial pressure will be greatest in the one with the smallest molar mass, which in this case is hydrogen, or C. Okay, now the next question that was most missed is number 25, I believe. I have to go down one sec. Yes, 25. A sample of helium gas and 2.0 millimoles effused through a pinhole in 53 seconds. The same amount of an unknown gas under the same conditions effused through the pinhole in 248 seconds. The molecular mass of the unknown gas is blank grams per mole. Now, anytime they're talking about effusion or diffusion, it's those 2 versions of the Graham's law. It's either rate over rate equals molar mass over molar mass, square root of molar mass over molar mass, or it's time over time equals the square root of molar mass over molar mass. And in this case, we are dealing with times, and that's clear because they give you the time in seconds. But the one thing that you don't need is those millimoles. We don't need millimoles. That's extra info, and I think many of you got a little consumed with that. So I'm scrolling ahead to show you my work. If you look at number 25, because it's time, you put time A over time B, and when you do that, you put the molar mass of A on the top because you had put time A on the top. And remember, it says that the helium got out in 53 seconds, but the unknown gas got out in 248 seconds. So the helium got out faster, which tells me it's the smaller molar mass. So you put the smaller molar mass on the bottom, so 4 grams per mole, and helium's time also goes on the bottom on the left side, which was 53 seconds. And then the time of the unknown was 248, and then obviously that equals the square root of molar mass A on the top. That's the one you're trying to solve. So in this case, what you need to do first is just 248 divided by 53. But if you do that, you will not get the number I wrote below, this 21.89, etc. Because you have to remember that to get out of this, you're going to need to square both sides. And so when you take 248 divided by 53 and square it, that's how you get 21.89. And then, of course, you want to cross multiply to solve this. And so when you do that, you get 88 grams per mole, which is how I got the answer. So those are the most missed questions, and I will make sure that the key is posted soon, and then Mr. Zamora also has a copy if you'd like to see other questions. And that's it.